Okay, so in this lesson, chapter 3.3, what we're going to learn about is graphing and solving systems of linear inequalities. Now, as we see here, as in the notebook, in the textbook rather, says, we see a system of linear inequalities. In chapter 2.6, we learned about linear inequalities. In chapter 3.2, we learned about linear systems of equations. But now we're looking at linear inequalities, graphing a system of linear inequalities and solving them, using that to solve. How we solve linear inequalities will be from graphing. We will not be using the elimination method or anything for this section. So like a linear system, we can find a solution to the system through an ordered pair that is a solution to each inequality. So as an example here, we have 3, -1 is a solution to both of them, as 3 plus -1 is going to be equal to 2, which is still less than or equal to 6. And if we were to use, that was that one. If we were to use this one, we have 2 times 3, subtract -1 is greater than 4. 2 times 3 is 6, that becomes a plus, and 7 is indeed greater than 4. And so this one is a solution. But there, in essence, an indefinite amount of inequalities or solutions to this system of inequalities. And so how do we find out this, all the different types? We're going to do that by representing them on a graph. So just to recall what we learned in chapter 2.6, to graph a linear inequality, or therefore a system of linear inequalities, we need to make sure that we know which graph corresponds to each inequality. And so remember, if it's a less than or greater than, we use a dashed line. But if it's a less than or equal to or greater than or equal to, then we use a solid line. So very similar to chapter 2.6. Now the difference here is what we're going to do is we're going to lightly shade the part of the inequality that matches what they have in common. And so that's the region that we're looking for. We're going to shade the region, and we could use colored pencils, but I prefer just to make it look neater by just trying to think through it like we did in chapter 2.6. And so you could use color pencils for this section. If you prefer to do that, I'll show you an example of how to do that. You can use a colored pencils so you can represent each inequality. So if you have 4 inequalities, you might want 4 different colored pencils. Uh, and so what happens is you want to have the region that is in common that has all the colors intersecting. All right, so it'll make more sense once we see it, so let's get to it. All right, in example 1, we're going to graph this linear system of inequalities. And just like we learned in chapter 2.6, we graph them the same way we would with a linear equation. But when we get to the signs, that determines if it's a solid line or dashed line. So because they're already in slope or intercept form, it should make it really easy. The first one, the intercept is at -1, and then it's going down 3 units and to the right 1, or you could go the opposite direction and go up 3 units. So that would be up 1, 2, 3 units, up, and then 1 unit to the left. And since mines are spaced out, I have to be really careful. All right, because that's a greater than or equal to for the first one, we want a solid line to go straight through these points. Remember, use a ruler where you can. All right, so that's our first one. Not as neat as we wanted, but with a ruler, it will make it really easy. All right, and then the second one, we change the color there, make this one blue. The intercept's at 2, so that's where it's intersecting. And then it has a rise over run of 1 over 1. We can go up and show it on the graph, so we'll go down 1 and to the left 1. So down 1, and I don't want to put an X there. Down 1 and then to the left 1 will take us down to here and then over here. Right, down 1 here and to the left 1 there. Okay, so we want to draw a nice dashed line because this is less than or equal to. So this one will have a dashed line going throughout, and the arrows to indicate it goes on indefinitely into infinity. All right, so we see the intersection, but the intersection's only one point that is in common, right? And then technically, you don't want the point here because that's a dashed line, so it's not technically included all the time. So you want to be careful there. So how do we show all the different types of solutions that could work? Because there are many solutions that work for inequalities. Well, remember we did shading last time. And what we did is we looked at the intercept and we used that to indicate where we should shade. And so if you look at the very first one, and I'll do that one in red again. If you look at the first one, it says greater than or equal to. Well, remember this is a y unit, so we could use that to help us to judge. Greater than that -1 is going to be everything above here, or above the y line. So basically it means everything on this side. Right? So hopefully you remember doing that. And so this is where you want to use your colored pencils. So that's everything that's there. Now for the blue line, y less than x plus 2, we can use the y-intercept to help us again. It's going to be every value that's less than the 2. Well, less than 2 is down here, right? Down this side. And so it's going to be everything less than this line. Less than every y value that represents that line. But you notice now we are actually overlapping. That's the stuff that's in common. And the stuff that is in common is what our answers or solutions to the inequality would be. So if I was to like draw this using purple, you can see that this is our border. Let me try to stay on line. That's our border, right? The line of y less than x plus 2, right there. And then also what is greater than this line 3x minus 1. And everything in this side is our region. And because blue and red make purple, I'm just shading over the part that's in common as purple. So that's our region. And any point that we choose from this region will satisfy both of those inequalities. If I choose something outside, like in here, this would only satisfy the blue and not the red. If I choose something here in the red region only, it will satisfy only the first inequality and not the second. But any points, as I'm axing here, any point here, and you can check this on your own, any point that we choose in here will satisfy the inequality. All right, so that's how you can use the colored pencils. So in this next one, we're graphing 3 inequalities. And so notice the first one is x greater than or equal to 0. We learned how to draw the line x equals 0 in the first chapter, I believe, or the first part of the second chapter. And so first we want to draw a line at x equal to 0 there. And because it's a greater than or equal to, it's going to be a solid line. So let's start off drawing that one, x greater than or equal to 0. Remember, that means a straight line, a vertical line through 0. So basically our y-axis is going to represent that border. So instead of drawing over the line, for me, which would be a little bit more difficult, just note that there is a line going through the y-axis. And that's what we're going to indicate as red. All right, and then remember y equal to 0, that's the line that we draw. And because it's y greater than or equal to 0, that means it's a solid line as well. And because our solid line is already there as the x-axis, we could just keep that there. And this is one reason why, as I looked at the equation already, just have the first quadrant here. The x and y represents those two boundaries. All right, so that means we only need to draw the other line since the other two are our boundaries. Now, if those was x less than 0 and y greater than 0, we would need to indicate that for sure with dashed lines. But because because they're both solid lines, we don't really need to have anything drawn there because they represent our boundary. All right, so let's go ahead and draw in the second equation. It's already in the x and y intercept. So remember, to find your x-intercept, set your y equal to 0. You're basically left with 4x less than or equal to 0. Less than or equal to 24. So to find the x-intercept, we're going to have 4x equals to 24. Divide both sides by 4. And 24 divided by 4 is going to give us 6. So that equation will touch at x equals to 6. All right, remember to find the y-intercept, and I'll keep the same color because we're going to have all the lines different colors there. We're going to need one line. So y-intercept, remember, you can set the y equal to 0. And just for convenience, I just scribble that out. So we're going to have 3y equals to 24. Remember, we use equals because we're actually seeing where does it touch on the x and y axis. So we actually use equal signs. Divide it by 3 on both sides, and so y is going to be equal to 24 divided by 3, and 24 divided by 3 is 8. Alright, so on the y-axis, I am intersecting at 8. So we see our borders, our x and y axis. We draw a solid line. Alright, so now we want to use our understanding of inequalities. And so if you want to use all the different colors, remember, first x greater than or equal to 0, because their x value is the y-axis, x greater than or equal to 0 will be everything over here. And because I have that other line as red, let's use it as purple, it would be everything in this direction, right? That's x greater than or equal to 0. Right? Everything greater than or equal to y would be everything going up like that. And then this one here, you could use a test point. You could choose a point over here. That's how it's shown in the book. Choose a point on the outside of that line and one on the inside of that line. And whichever one is true is the part that you shade. That's how you could do it if it's an x and y intercept form. Or you could change it to y-intercept form, and you could just use that method. So if you was to do that and just bring that negative 4x over, you can already see that you're looking for everything that's less than. So it's actually going to be this one here or this side. And just remember, if whichever point you choose, any point on the outside of those boundaries would decide where to shade if you do it the algebraic way. Alright, so if you were to shade in there, that's going to be in this region. You see what's in common is bounded by the x, the y, and the line. And so that's my region. So any point inside of here, any point that I choose inside of that region, when I substitute it into each of those inequalities, it will be true. Now, as I said, I did want to show you how to do that without a calculator and without hopefully erasing everything, but it would just be easier to do that. So I think we had 6 and 8 was our intersections. So 8, 6, and so the other way you could do it is just to try to think about in your head that x greater than 0 would be everything over here, right? Just kind of visualize it in your head. And that y greater than 0 would be everything over here, which is why we only have the first quadrant. Once you draw the second line that's here, then, which is that, you just have to determine which side you're shading on, because you already know you're shading this whole region. And so because all of this region is satisfies the first two inequalities, then you need to decide from this inequality, is it on this side or this side that everything is in common? And so the more you do it, the easier it gets, so you don't have to have all this shading. And so once I decide which side we're on, we're done. And so you could use your understanding, as I said, picking a point either here, and any point will work. If you pick the point that I just had there, 2, 4, and substitute in there, you see 2 times 4 is 8, and 4 times 3 is 12, and you add those two together, it's less than or equal to 12, and so you could shade in there. Or if you chose a point, out here, let's say 5, 7, 4 times 5 is 20, 7 times 3 is 21, and that's less greater than, so it's false, so you know to shade in here. And because that's your common region between everything, you can just go ahead and shade. And so like I said, the more you do it, the cleaner it looks and the easier it gets using these shorter methods. Alright, let's look at this third example here. This is not in the book, but this comes from one of the questions in the exercise. But I did want you to see another form that can pop up. What's beautiful about this one, they're all in slope-intercept form, so no algebra is needed to verify anything. Alright, so let's go ahead and shade that. The first one, x greater than or equal to 0, would mean everything everything to the right of the y-axis. So you know you're shading somewhere on the right side. Alright, so then we go to the next one, y greater than 2x subtract 1. And if we do that, we could just quickly graph that using slope-intercept form. All right, so let's do that. We have here 2x subtract 1. Negative 1 is our intercept, and rise is up to 1, 2 over 1. Up 2 over 1. Up 2 over 1. This just makes it easier to graph, and down to the left 1. All right, so we can clearly see what. And for that other one, I should have labeled those graphs. Forgive me for not doing that. All right, so this one should have been a dashed line. When we write the equation, we want to label it, since it's more than 1. So y equals 2x subtract 1, and we're writing the equal sign just to show that's the actual line that we've drawn. The second one is a solid line, and this one we can graph going to 3 on the y-intercept. So 3 on the y-intercept, and we're going up 2 and over 1. So up 2 units, and this one, as you can see, is parallel. Up 2 units and over 1. So you know parallel lines do not touch, as we learned before. Down 2 and to the left 1. Down 2 and to the left 1. So what, and this is why I chose this one. This one's a solid one. So drawing a solid line if my pen doesn't get turned off. And make sure you use a ruler. Comes out really nice. And that's our y equals to 2x plus 3. All right, so now we just need to do our shading. We know it has to be to the right of the y-axis because it's everything greater than that. And remember, when we draw lines that are x equals to, it is parallel to the y-axis. And because it's at 0, it's actually the y-axis. So that's one of our boundaries. So we know it's everything to the right, or part of the first quadrant. And then not only is it greater than or equal to 0 there, but it also has to be greater than the 2x subtract 1. And because I don't know where you stand, I can't ask, I'll do the shading of everything. So since that one's, I circled it blue, let's make that one red. So I'll do the different color shadings, just to be on the safe side. So that's red. Let's make this one green. All right, so everything to the right of that is green, and you could actually color it in. Some students will color the whole thing. That's just going to take too long. So little lines there just show that it's shaded. I think 2x minus 1, I have it as red. So everything greater than that negative 1 is everything up here. So that means I'm shading all of this, right? Everything greater. That blue line is not my boundary. So we're shading all of that. All right, so, and if you want to color that in, you can. It's going to take some time, but it can make it look a little bit neater. All right, I have some overlap, so I just want to clean this up. Shouldn't have any overlap over that boundary. It should go right to the boundary, but not past the line itself. All right, and then the last one, I think it's light blue, sky blue, baby blue. All right, and this one is less than or equal to, and we could use the y-intercept to help us. And somehow my line is going a bit crooked there. All right, and so that's everything less than the 3. So everything down this way. And then you're looking for just that which is in common. So hopefully you can see that this one here, the boundary, I'll see if I could draw it in purple. The boundary, of course, where everything is in common. This line is where it stops, where everything is in common, right? Hits it to the 3. Then it comes down like this, right? That's where you see everything in common, right down till we hit to that axis. And then right here, this blue part, purple part shouldn't be there. And then back up like that. So that's our bounded region. Right out, unbounded, right? It goes right out. There's no bound there, and that's why you see me put unbounded. And so this one, everything that's in common is like that, right out to infinity. So there's an infinite amount of values as there's no bound. It just keeps on going up. But that's how you do it with all the shading. The more you practice the theory behind it, the easier it will be not to have to shade all these different things. And it gets much easier and much cleaner as well.